So in chapter 3, we're going to learn about molecules and compounds. We'll learn about the types of compounds. We'll learn how each type of compound gets named. And then we're going to look at how experimentally we determine the chemical formulas of compounds. The first half really represents sort of one lecture, and then the second half, the determining of the formulas of compounds experimentally. That's kind of a whole separate thing, sort of, it's more quantitative. The first part involves a lot of memorization, so I would encourage you to, if you haven't really memorized the names of the elements and of the polyatomic ions at this point, I would really encourage you to work strongly on that so that you can recall them quickly and you don't make mistakes, like, for example, mixing up sulfate and sulfite. All right, so let's get started. There are really only two types of compounds. So compounds are either classified as ionic or they're classified as covalent. Now, in ionic compounds, like the name says, it's made up of ions, and ions fall in two categories. They're either positive ions, which are the cations, okay, or the negative ions, which are the anions. And we talked about this in earlier chapters, that from the periodic table, we can look at an element's position and determine what kind of ion generally it will make. So cations are the metals, and they lose electrons. And then anions are generally nonmetals, and they have a stronger affinity, is the word we use, a stronger affinity for the electrons, and so they're able to pull the electron away from a metal. So nonmetals gain electrons. And remember, the electron has a negative charge, and so that's how you get the negative charge on the anion. If you look at a periodic table, again, just a quick reminder, the cations are formed by the metals, which are all of these I'm sort of highlighting with this cursor, right? And then the nonmetals generally are these, and those are the ones that form anions. The semimetals, like silicon and germanium, arsenic, antimony, tellurium, those guys typically are negatively charged when they form ions. Okay, so the semimetals generally form negatively charged anions as well if they form an anion. Okay, so back to the slides. So covalent compounds are typically composed of nonmetals. And so we have nonmetals. Both of them have high affinities for the electron, but because one isn't much stronger in its affinity for the electron than the other, because they're both nonmetals, as it turns out, they will share the electron. So we tend to say nonmetals are sharing electrons, and then ionic compounds are with a metal and non-metal are unshared electrons, and that's how we get the formation of ions. Okay, so this is just sort of a picture. It's a graphic from the book. It gives you sort of the depiction of how this whole process works. You have chlorine in molecular form, Cl2, but what ends up happening is the chlorine's affinity for the electron is so much higher than the affinity for sodium. When the two run into each other, it ends up being that the chlorine removes the electron from the sodium. Now, if you remember, the driving force, and one of the reasons we say was the driving force for this process, is that sodium then gets to have same number of electrons as the noble gas neon, and chlorine gets to have the same number of electrons as a noble gas argon. And we base, again, the charge that they get based on their periodic table position, okay? Now, when an ionic compound forms, when we think about how those atoms are arranged, because they're just positive and negative charges, what they end up doing is clustering together like it's shown over here in their solid form, and that creates the crystal structures that you see in a lot of ionic compounds. The crystal structure for sodium chloride is cubic, and if you ever look at the shapes of the crystals of sodium chloride, you'll notice that they all are shaped like little cubes, and that comes from sort of this aggregation of positive and negative charges to form the crystal structure. I should also point out that when you look at the structure of sodium chloride like this, there is like no distinct sodium chloride unit. The whole thing is sodium chloride, right? It's just that what the formula sodium chloride tells us is the ratio that you need of sodium to chlorine to get a neutral charge. So I'll just put a little note here. The formula that was weird. NaCl simply represents the ratio, right, to get a neutral charge. And that the actual structure of sodium chloride is just this big sort of network or crystal structure that you see, which is reflected in the shape of the crystals. Now we're going to watch this quick video because I do want to make one more point about when two elements react. Okay, the properties of the compound are very different than the properties of the element, and we can see that when we watch a video of sodium chloride. That's table salt, right? So this is table salt being formed. So there's no sound in this video, so I'll sort of narrate over it, but they will have stuff on the slide screen for you. Let me go ahead and make it full screen. I think, oh, it was full screen. I think the way I have it set up, you see most of the screen. You're not actually seeing all of my computer screen. So reaction between sodium metal and chlorine gas. And then I'm going to recommend a video for you to watch. It's a little longer, but it's interesting. So that's chlorine gas, and there's a number of ways you can generate it. Like pool bleach can be used to generate it, but it's very poisonous, so you have to be careful. But you can see it in here. It has this sort of greenish color, and that's a piece of sodium. So sodium metal, I don't know if you can see it in the video here when he moves his hand away. Yeah, when he picked it up, you can see it. It's actually shiny. And what he's going to do is he's going to pop it down, or she, I actually don't know, pop it down into this chlorine gas, and he's going to add a drop of water to it because the sodium quickly in air gets coated with oxygen and forms a sodium oxide. So you need a little water sort of to activate it. So did you see the bright flash? Of course you probably saw the bright flash. The bright flash was the formation of sodium. And let me pause this real quick. Oops. Oh, that's funny. Oh, they're going to play it in slow-mo. That's the drop of water going in. I'm going to pause it here, just so you can see this. All this white that you're seeing in here, or this cloud, that's actually sodium chloride, tiny, tiny crystals of sodium chloride that are formed almost like fog. Right? It's very similar to fog, actually, in its behavior, but a very fine mist of salt crystals floating in the air. So they formed from that flash of energy, right? So chlorine gas is really deadly. It's green. It's a gas, right? Sodium is super reactive with water. But then if you saw, right, if you're familiar with table salt, you realize like that's what we eat, right? And it's not reactive. It's not shiny. It's not green, it's not poisonous. There's a number of things that are different about sodium chloride. So the properties of an element, okay, are very different from the properties of the compounds that they form. And then I'm just going to recommend this video here. This video is by Nile Red, and if you're not familiar with Nile Red, he does a lot of really cool like chemical reactions. Anyways. But his video on making sodium chloride is one that you should probably watch. It's very interesting. Okay, so let's look at covalent bonds. Covalent bonds is the sharing, quote unquote, of electrons between two atoms. Primarily occurs between two nonmetals. Okay, so what ends up happening is that the nuclei of atoms, supposed to be represented by positive charges, right, are attracted to the negative charge of the electrons of each other, actually. So each one has an electron. Usually they contribute to this covalent bond. And then what ends up happening because of that is the two atoms stay stuck together. Now, there's an idea, it's called Coulomb's law. It's the idea of opposites attract. And basically, the closer you are to the opposite charge, the more stable you become. And so your book goes through a couple of different scenarios of, well, where will the electrons be, right, if you have two atoms making a covalent bond. And I think you can visually get the idea that when the electrons, the negative charges, are between the two nuclei, that's when the force of attraction will be the strongest. And so this force of attraction is what we call a covalent bond. Now, like ionic compounds, when you form a covalent compound, the properties of the element are very different from the elements are very different from the properties of the compound. Now, when you form a molecule, and this is what we call substances that are held together by covalent bonds. When you form a molecule, they form unique units. Unlike, right, in ionic compounds that form like networks or crystal structures. You can form crystal structures with molecular compounds, but there are independent units within that structure where the atoms always stay together. In an ionic compound, it doesn't care which positive ion or it's next to or which negative ion it's next to. Just a real quick video again, and then I'll move on. Oh, I did want to point out, as I should, this is the link, and this video is nice. They're very plain, but this particular content creator, his stuff is very straightforward. So if you want to see a bunch of different reactions in a row, you're able to just like watch him. He doesn't spend hours talking about each one, which is kind of why he gets used a lot, I think, in lecture videos. Okay, so let's look at this real quick. We have a hydrogen balloon, so he's going to generate the hydrogen by putting aluminum foil into some sodium hydroxide, or you could also use hydrochloric acid, but sodium hydroxide really works well. It takes quite a bit of aluminum to make enough to fill a balloon. I was talking to an older instructor who grew up in the 40s, so he was quite a bit older, and he would make this mixture in his garage, and then he filled up a big rubber Goodyear blimp that he had ordered by mail. And he did this for days, filling up the blimp. And you can see there's a slow reaction. The balloon has to be pretty thick, otherwise the hydrogen sort of leaks out of the balloon surface. But he and his friends, it was in sort of North Fresno at the time, which is really the middle of Fresno now. They lit it on fire. So they had a rope they tied to it, and it floated up, right? And they thought it was going to explode, but it just floated like that balloon did. It just went up to the ceiling. Here's a picture of the ceiling. So it didn't explode like they were hoping, but then suddenly they had this giant rubber balloon on fire floating over Fresno. So that is the reaction of hydrogen and oxygen to form water. So hopefully you've gotten the idea anyways, that if you have molecules, right, that form from different elements, the properties, again, of the elements and the compounds are very, very different. Okay, so the next thing I want to do is do a little bit of practice. And the last one we haven't covered, and so you're going to have to think about it a little bit, but you have a formula down here. Hopefully you recognize this is sulfite down here. Identify whether or not the following combinations make ionic or covalent compounds. I'll go ahead and pause it. I did include a periodic table here, and we'll see how you do. Okay, so I could have color-coded the answers. Uh, Oxygen and nitrogen are both nonmetals, right here. And so two nonmetals will make a covalent compound. Carbon and magnesium, right? Carbon and magnesium, metal, right, and non-metal, so those will be ionic. And then barium sulfate, you have barium and barium sulfite, I should say. You have barium, and then you have sulfite. Now, if you recognize sulfite right away, you know the type of compound it is because sulfite has a 2- charge, so it's an anion, right? And so the compound barium sulfite is an ionic compound, has to be because of sulfite. So there's two types of compounds. There's ionic compounds and covalent compounds, and ionics for metal, nonmetal, or ions, right? And then in the case of sulfite, for example, and then the covalent compounds are all nonmetals. Now, beyond that, we actually have other ways of representing compounds, and those are chemical formulas, right? And there's different kinds of chemical formulas. There's the empirical formula, the molecular formula, and the structural formula. The empirical formula tells us the ratio of elements. Now, this is actually what you're seeing when you look at formulas for ionic compounds. All ionic compound formulas are empirical formulas. Simplest ratio of elements. So like sodium chloride, NaCl, is actually this giant complex of, trillions of sodiums and trillions of chlorides. But the simplest ratio is just one sodium for every chlorine. So that's what we're talking about. The molecular formula is used to describe covalent compounds, and it shows the actual numbers of each element in the compound. And so we, again, for molecular compounds, is what we use that for. And then structural formulas are similar to molecular formulas. They show us the exact numbers of elements in the compound, right? So it follows sort of this idea. But it also shows the shape of the molecule and how the atoms are connected. So plus shows shape and how, because remember, atoms are connected by those electrons that sit in between to form the covalent bonds. So it shows the shape and how atoms are connected. So how do you tell whether or not it's molecular or empirical, right? First of all, right, you can't have subscripts that are fractions, so they have to be whole numbers. And if you look, for example, at this compound, Na2S2O6, if it's an empirical formula, you can't divide these by a common factor and get a lower number. So for example, in this one, I can divide by 2, right? That means it's a molecular compound. It's representing the actual number of atoms rather than the ratio of atoms. So for example, if I take this is molecular, let me write that down. If I divide that by 2, then I get the empirical formula out. That's NaSO3. So it can't be reduced anymore, so that would be an empirical formula. So this is empirical. What about P2O5, right? So let's look at P2O5. Can it be reduced anymore? Well, if you know 2 and 5, right, even and odd, well, you can't divide by anything to make it a lower whole number, right? If you divide by 2, the O would be 2.5, for example. So this is the empirical formula to begin with. Well, now what about C6H12O6? So this might happen to you, for example, on like a quiz or a test or something like that. Uh, is that empirical or molecular? So you might think, well, maybe I'll try 3 first. I'll divide by 3, right? And what you're going to get is you're going to get C2, and then 3 goes into 12 4 times, so you get H4, and then O2, and then you'll recognize, oh, those are all still divisible by a number, so we can divide that by 2, so we can divide it by 2, right? So this is divide by 3, we can divide by 2, and then you'll end up with C, H2, and O. So this is a molecular formula. You know, you have ones here, so you can't reduce it anymore, so this is the empirical formula. And what this 3 here and this 2 are telling me is I could have just divided by 6 in the beginning, but you might not see that, right? So just find something that's commonly divisible by. If you need to get the empirical formula, then look what your result is and then see if you can find it again. So this brings us to structural formulas, and in a way, structural formulas are molecular formulas. They have some similarities in that a structural formula gives you the exact representation of the atoms in a molecule, but it also shows you structure, and it shows you how those electrons bond the atoms together. So, for example, this is H2O2. This is a structural formula, right, with a pair of electrons bonding the hydrogen and oxygen, a pair of electrons bonding the 2 oxygens, and a pair here bonding this oxygen and hydrogen. So it can just show how it's connected, but it can also show geometry, try to and give you the impression of geometry. The angle on these, is about 109 degrees. It's a little bit less than that probably, but let's say about 109. This angle is 109, and so it's trying to give you that sense of the shape of the molecule. Still, on paper, it's two-dimensional, but to give you the sort of feel for the shape of the molecule. So the type of formula that we use just depends on what we're trying to communicate about the compound. Do we just want to know its composition? Then that would be like an empirical formula. If we want to just know the number of atoms, that would be a molecular formula. The actual number of atoms would be a molecular formula. If you want to know the shape or how things are connected, then that would be a structural formula. And again, empirical formulas are really the simplest formula. They communicate the least information, and a molecular formula gives us the most information. Or a structural formula gives us the most information. Now we also have what we call models, molecular models, and we have modeling kits. And these are kind of like physical representations of structural formulas. And what you have is you have atoms. Every atom has a color associated with it, and the color code is shown on the right. They try to show relative size, but typically, for example, sulfur and chlorine, now they're different sizes actually, but they don't try to make exactly that kind of representation, but they give a color code for it. And a molecular model is like a more accurate structural formula because it shows you like a physical shape of the molecule. You have to remember when we do things like this here, right? This is actually, even though we're trying to represent it, is actually two-dimensional. And so in molecular models, we have like a ball and stick model, right? And we have space-filling models. Models try to represent three-dimensionality. And then you can actually buy kits that have the atoms with the color codes to show the actual shapes of the molecules. Okay, so just a very quick overview, the atomic sort of level view of elements and compounds, right? Pure substances, we have elements, and then we have atomic elements like neon or iron, for example, are atomic elements. We have molecular, which are elements that are molecules, and then we have compounds. And molecular compounds, you have these distinct units that float around that have a specific number of each type of atom in them. And then you have ionic, which is just really the representation of the larger structure of the ionic compound. So this sodium chloride unit, for example, is the smallest unit. It's actually called the formula unit of the uh, ionic compound. And the actual structure of sodium chloride really looks like this. Okay. So most elements exist as atomic elements. Examples, like I said earlier, there was neon and iron, but sodium. So the majority of the periodic table is ionic. And then we have molecular elements, and there's actually 7 which are diatomic. And so we'll pull up a periodic table here. Okay. And the 7 diatomic elements are these. I guess I'll highlight in green. Starting with nitrogen, right? Well, that's actually not green. Nice. And then these. Okay. So those are 6 of the 7. And notice it starts on 7. It's not hard to remember these, but it makes a 7 on the periodic table. It starts on element 7, and then the other one is hydrogen over here. So the diatomics are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Now, phosphorus and sulfur, these are also molecular elements. Phosphorus exists as P4. And sulfur exists as S8. And so as a molecule, it actually has 8 atoms sort of in a octagonal structure. It's kind of a folded octagonal structure, but it's an octagonal structure. An octagon would be like a stop sign shape. So there's actually 8 sulfurs connected. In phosphorus, they make a tetrahedral arrangement where there's phosphorus is connected sort of in a tetrahedral sort of geometry. But anyways, and there's 2 different forms of elemental phosphorus. We can talk about that some other time if you ask. But yeah, phosphorus is P4, and sulfur is S8, and these are your diatomics. So that's the summary of chemical types of chemical formulas, representations, and then also giving you the idea of atomic and molecular elements. In the next segment, we'll talk about naming compounds, and we'll go through each type of compound and look at how those are named.